had to go through reconfiguration of Zoom for some reason. Who knows why?
Yeah, okay, fine.
We shouldn't do future programming. We should do future of web conferencing. That's a real problem.
Yeah.
So, how are you, Vlad?
Huh?
How are you?
I'm fine. I don't know. You?
Good, thanks.
Yeah. So we were talking about like collaboration topics, decision making, reasoning, design rationale. Yeah. Do you think it's better to introduce, like, make small introduction first? Like, although I remember you were talking in the first online meeting, still it might be helpful.
Sure. Do you want to go first? Or?
You can go first.
I'll go for it. So my name is Duncan. I started programming when I was like 8 years old or something. So BBC Basic on the Acorn. Motivation was to make games. And I think the biggest motivation to start programming was that it was just a mysterious thing. And there was a book with a spaceship on the front. And whilst I was playing games, I would sometimes flick through it as a little kid and go, what on earth does all this mean? Until one day I decided to try out the set pixel routine or something. And I got my first like magenta dot on a screen. And I felt like God, basically. And so that's, I sort of programmed for fun and made little games and things and studied computer science. That was getting on for 20 years ago. Since then, I've worked in various places, sort of defense and finance, but also creating satellite control systems and in renewable energy, doing various work like creating design tools for engineers. So for designing wind turbines, for designing control systems, for planning.
Wind turbines?
Wind turbines. So windmills.
Okay. Turbines.
Turbines, yes. And planning wind farms. So optimization of how you lay out multiple wind turbines across a landscape to maximize the energy capture from a flow of wind. Yes, and creating the actual embedded control systems themselves. In that role, so created a lot of different products, but also made sort of software teams. So I've taught and seen how teams of software developers work. And these days, I'm one of my main interests is in design and is in sort of design tools. And I guess my closest interest to future programming is less to make sort of programming easier, but it's to make design easier. So to me, that's always been the much more important aspect of programming is software design. And for me, a lot of the aspects about syntax and programming languages are often immaterial compared to how important it is to get design right. And that's why I'm building Thorny, which is a decision-making tool, which we can talk about more if we want.
Yeah.
And because of the way it works, it's at its heart, it's very much in the same realm as projectional editors and those sorts of things. It's all the sort of future of programming topics are actually relevant to building a design tool, programming tool. But yeah. So how about you?
Okay. Well, I started to program like when I was 13, I guess, or 14. Yeah, I also tried to do some games like Visual Basic, just basic. Pascal. Then I tried to learn other languages. Yeah, at some point I want to learn as much as possible because I just liked that many different languages like have different capabilities, and I was just curious about expressiveness and everything. And I was like, at some point, was really like crazy about functional programming and metaprogramming. Then I realized that nothing magical about it. Then at some point I wanted to create my own language, but then I realized that there is no use in creating one, because like basically what I could do at that point was just like some kind of clone of Scheme or Python. Like it doesn't make sense. Like there's already a Scheme or Python. Like I should solve new problems to make something really useful. And at some point I was stuck because I didn't understood what are the problems. Yeah, and then I stumbled upon Brett Victor's, and suddenly I realized that, like, I learned that programming is not just like text in the rectangle that like you type in and it works. It's something much more flexible and bigger, and who knows how we're gonna program in the future. And I realized that, yeah, really making this computer-human interaction like more optimized, like really optimized, effective. That's a good problem to solve, and if I can do some progress in this field, it's gonna be useful, it's gonna be great. So that's what I'm thinking about. Yeah, and right now I work as a programmer like for I guess 7 years already or something, and recently I realized that I want to become an academic and trying to enroll to university.
Okay.
Yeah, that's it.
And so what have the projects been that you've been working on, the programming?
You mean like as my job or like my experiments?
Yep. Just sort of the languages and types of software it's been.
Okay. Well, at the beginning, I was trying like I had some like about 2 or something years of Ruby on Rails like production, like well, web services, everything. Then I worked at one interesting company that developed a video streaming media server in airline. It's called FluSonic. Maybe you heard, maybe not. Yeah, but it's like software that like ingest video streams, different protocols, and serve them to 1,000 clients and video archives and like things like that. Yeah, and it was really interesting. I learned like a lot. Yeah. Now I'm working in one company that creates like some kind of marketing tools, not real marketing tools, but tools that can like improve the profitability of the businesses. And there is a lot of services in Clojure, but I don't really like Clojure. It's for me it's too complicated language.
Mm-hmm.
Yeah. Yeah, just that's the language that I worked with, but there are many that I tried and left and left them. Yeah,
that's interesting. So what have you found the problems to be in programming? What are the sorts of things you would like to fix?
Well, one of the problems that I mentioned in the like previous one-on-one talk, and I think that's the first one, is that inefficient abstractions, inefficient for humans, because they might be efficient for computers, but they're not efficient for humans. There are some patterns, some rules that it's not really about syntax or interface or anything, but even the abstraction itself might be not convenient for humans to work with. Yeah, and I'm trying to understand what are the rules and how it should look like.
Do you have an example in mind of an inefficient abstraction?
Yeah. I think I provided also the previous talk. It was, for example, you have this thing, this function, like you sort of understand. This is a thing. You put some data, it returns data. Like if it's pure function, you understand what it means. Then imagine have Clojure that captured socket, for example. It's like some function looks like function. You take it as a function, but its behavior is totally unpredictable because it does I/O that totally shielded from you. So basically, what you have is that you hold some kind of object that you think you know what does, but it does something totally unknown. And you see no explicit connection to the behavior. So this is kind of abstraction, like closure that captures input output is really, I think it's not effective and really strange. It doesn't align with our everyday experience.
Mm-hmm. Is that something you experience in real work, that problem of a function?
No, I'm not sure. But I experienced some. No, I'm not sure. I'm not sure.
So I think it's always interesting to sort of, there's an interesting gap between the sort of things people talk about in future coding and then the real things that happen to give you a bad day in a day of software.
Yeah.
And there's often a big sort of gap for me. It's like sort of, if there's been a terribly difficult problem I've had to solve, it wouldn't have been something that would just been magically easy with pure functions or something. It's just sort of
yeah. That's true.
It's the sort of it's almost always third-party dependencies. It's almost always that there's elements of configuration and behavior that I don't understand and may not be working properly, and I'm having to learn 4 things at the same time, and it's the whole dependency management issues. Those are the sort of practical things where something doesn't work as you believe it should. I wish for sort of more, there should be a list of what are the problems of programming, and there should be, maybe Steve has one of these somewhere on his wiki or something, where everyone can sort of see the list and go, my God, yes, just solve that one, and I'd have saved a week last month.
Yeah, but it also would be great to actually agree on that kind of list, because for one is the problem, for the other is just something that they want. For example, for me, I find macros as a great problem, because at first they're really cool because they give you like incredible flexibility, but if they're not restricted, like if their use is just encouraged, then you end up with really complicated code. And it looks like function, but it's not function at all, right? It's often, and it's really hard to. You have sort of 2 spaces to debug in: the text editor and the expanded macro, and it's really complicated. So.
Yeah, I think there's a whole class of cool features in programming languages, and cool is basically danger, red flag. Thing you have to ban in the coding standard. It's operator overloading. It's template metaprogramming to the nth degree. It's there's
But maybe there is a way to like cut this feature into 2 layers and like make a clear distinction. For example, in metaprogramming, if you make it really special and complicated, like not complicated and hard. So to write a to write a macro, you really have to have a good reason. Like you really have to go through some kind of struggle to write it. So people wouldn't do it casually and wouldn't create like problems where they shouldn't be. For example, and I see that kind of attitude in Erlang programming language, because actually you can have macros in Erlang, but do you have to write a parser transformer or something like that? So sometimes people do if they really need it, but most of the time it's pure functions, it's all clean. This way is better.
Yep. Some of the sort of techniques I quite like that I also don't hear much about more. I forget what it could be called these days. I'm pretty sure it has an official title, domain-driven design or something. But it's basically having data structures in a sort of in a format that isn't code, and using code generation to generate your various data structures in however many languages you have. Certainly back in the day, you'd always have your front end that would be in one language, your calculations that would be in C++. You might be able to push it in and out of files and databases and communication protocols and a million other places, and just having a lot of the important facts about your software, not in software, but generating software, was always a way just to be just so certain that everything was correct, and you wouldn't have a maintenance nightmare if you had to make a radical change, because you could just tweak the generation and recreate your code.
Consistency between different parts of system written different languages.
Yeah. So you could always choose the best tool for a job. So it was definitely not having one master language for every type of application, but not feeling like you were going to incur a massive cost by using a different language. You could specialize to a particular problem. And I think that concept does get closer to the ideas people have for future programming languages that have multiple representations. In some ways, you can have those multiple representations being the different languages we currently have today, and trying to extract some of the core facts about the software into another medium. But the reason why I brought it up was just when you said about having another mind when you're sort of looking at programming, because code generation was an example. It's probably effectively like macros done big. You're looking at your generation template and it's generating code. So you're executing the code. Yes. You have to know what code is being generated. You have to look at the generation code, and then you're also having that third aspect of needing to understand what the output is going to do when it's actually run.
Yeah.
So Brett Victor's playing the computer. You're actually playing the computer at least twice. So you need at least two brains whirring away. So that's the disadvantage of that approach, but it did make me think of your macro comment.
Yeah. Can you tell me more about, like, I hadn't worked much with embedded systems, and it's really interesting. So basically, like, what you were doing is Internet of Things or something. So you basically had different devices and communication between them and controlling.
Yeah. Right. Yeah. Okay. So for a wind turbine, what the control system does, I don't know whether I said this on the call or not, but I'll repeat it. So when the blades turn on a wind turbine, they create massive forces on sort of the mast and thing. You get things like a mast shadow. So each time it goes whoomp past the mast, it creates these vibrations. And the vibrations, build up, and they would tear a very flexible, gigantic structure like a wind turbine apart. So what a control system actually does is it uses the pitch of the blade to damp the vibrations in the structure. And so how well it can damp those vibrations means how fast the turbine can spin and how much power it can generate. So it's this very sort of subtle control loop to control pitch and reduce vibration. And if you get it wrong, the turbine destroys itself. It just pulls itself apart. So that's the really clever bit. And then there's an awful lot of sort of less clever, but still quite important things. So that control system connects to pitch systems. So pitch drives in the 3 blades. It connects to the generator, which can be variable speed, variable torque. So it's controlling the speed of the turbine with the amount of torque that the generator is demanding. And then, so we might have gearboxes and these sorts of things. We have a huge number of ancillary sort of systems. So there's everything from a light on the top to warn for airplanes and these sorts of things. And there's a safety chain, because this is obviously very big industrial equipment. which could kill people if they get in the wrong place. So it's all sort of a human safety level. I'm trying to think. There's a whole bunch of other systems. It's a few years ago since I built these things. There's various power supplies and batteries and these sorts of things, because it has to go move itself to a safe state if it loses power. There's grid connections, obviously. So the control system has maybe 1,000 input and output channels. Some of them are sort of just digital yes/no signals. Some of them are analog. So they might be the pitch angle or the generator torque. Those would be floating point number type things. And a control system is sort of it's often called a sort of PLC, programmable logic controller. And they look like long. They're quite fun to look at. You sort of Google them afterwards. They have a sort of CPU unit, and then they have all the I/O channels, and they all sit on a backplane, and all those I/O channels just have all the wires going in. So they're a total rat nest of all the wires for all the different subsystems. So me as the controller software developer has to basically sort of integrate all the various subsystems in the structure, and tell them what to do. So there's a lot. So each one has a state machine. Each of them has different sort of protocols to talk to. CAN bus or or they could be HTTP, all of those sorts of things, or they could just be a raw sort of signal. And then you're moving the entire turbine through various states. So if the wind picks up, then you want to start up the wind turbine, and you go through various states of turning sort of generators on and demanding torque and getting the pitch into the correct position and releasing brakes and all those sorts of things. And the startup routine is a bit like taking off for an airplane. It's very sort of similar. You have to catch the wind and not stall and not do any number of horrendous things that would damage the turbine. So you're sort of ramping up the speed until you get to rated speed, and then at that point you're all about trying to optimize the amount of power you can generate. So that's these very high frequency pitch movements to eliminate all the vibrations. So as a software developer, that means that you do have this continually changing set of thousands of input and output signals, because everything is a prototype, everything is changing. Your generator person will say, oh, here's the new version, we scrap those signals, introduce these ones, we've got a new state where, if it's too cold for 3 days, then it will take us an extra 6 hours to warm up. So, and you have to set this signal. It's like, what the hell? Now you have to, measure all this information to then bring a subsystem through a particular set of states. So it's a maintenance nightmare because everything is changing. And this is where one of those code generation approaches makes a lot of sense. So, what we did is have a spreadsheet full of a definition of all the signals, and these will be updated as things changed. And then we'd be code generating from multiple formats. So there'd be all various places we'd need to know information about these signals, whether it's configuring sort of the backplane and the control system and the hardware, or it's configuring, or it's actually in the C code of the main controller. Then we extended it quite significantly by having all the various sorts of alarm conditions. So every signal has potential, good and bad ranges, but then there's more complicated types of alarms where multiple signals go out of. For example, there might be two pitch, so there might be more than one sensor for the same value, and if they differ, then that indicates that at least one of them's broken, and we now know nothing about what's happening. So you're comparing a lot of the signals for consistency. If the blades are spinning very fast and the generator isn't,
something wrong.
Happening, it's these sorts of things where you then it's time to emergency stop. So there's a lot of state machines for all of these. So in terms of sort of future of coding topics, so it definitely is trying to describe all these complex things as data and then generating the code, instead of just having endless pile of imperative code that says if this then that. Some dude is jumping in and going, oh no, we forgot. We haven't checked this signal. It'd be a nightmare. So it's much easier if there's a table that says minimum value, maximum value, set of error conditions, what consequence should happen if it goes out of range, for one type of signal going out of range, it might just be a normal shutdown where you just gently, slow everything down. Another signal, it might be a freak out emergency, hit the brake. And yeah, these require a lot of review and study because if you do the wrong thing in the wrong mode, you're screwed. So the amount of state is frightening. And one step that did make that, it was sort of a prototype idea, but it stuck, was describing state machines in spreadsheets as well. So there's a lot of non-programmers who are having input into these things. And generated code for the state machines and then generated images as well. So in a factory floor, when testing a subsystem, would have printed out the actual state machine, and then there'd be the team of electrical engineers who don't want to look at C code, can then study images of the state machines of how we're running the generator, and they can go, oh look, if this then that. It's the sorts of reasons I wasn't too happy with this was because it did mean we did put C code inside spreadsheet cells.
Yes.
Try to limit it to just function calls or x greater than y, so just conditional sort of expressions. Obviously, it's a compiler ensuring that this stuff isn't all.
But
horrid.
was it convenient for them, right? Did they like the interface that you provided them?
The interface. Oh
yes,
yeah.
Like printed state machines, like
yeah. Well, I mean, for engineers to understand as we're testing things, yeah. But that is one of the other subsystems is touch screens. This was back in the day before iPads, so these were capacitive touch things. So yeah, generating information about the signals for the Java touch screens was one of the sort of many different categories of code. Yeah, and those were systems that typically used LadderLogic.
What?
And LadderLogic. So it's a visual programming language created in the 70s or so.
Okay.
And its motivation is to make programming look like an electrical circuit for the benefit of an electrical engineer.
LabVIEW, right? LabVIEW?
No. LadderLogic.
Okay, but it's similar, right? Is it?
So it literally looks like a very big ladder because it's like so I'm not sufficiently an electrical engineer to remember how to call it, but it might be a sequence of if you Google it, you probably
I Google it. Yeah, I see.
A sequence of sort of relays is sort of what it looks like.
I see.
In parallel, and that would be a ladder. And the idea is that then if your sort of factory automation system breaks down, then the handyman who can read electrical circuits can go in and change the software. It's one of those sorts of things that was sort of, I think there's theory behind it to be an abstraction that made sense to the skills that people had, but much in the same way that COBOL isn't actually a pleasant experience in natural English. Probably neither is LadderLogic, but it's absurdly unpleasant for a professional programmer. We're not talking type systems when we're talking LadderLogic. We're talking something, a simple expression that would be, half a line of code could be 2 pages of LadderLogic because it's sort of so verbose, in terms of images. So it was quite funny that there's those type of languages have multiple representations. So they recently added something that looks a bit like C. So, and you can basically sort of flip a toggle and it would turn your LadderLogic into structured text, I think it called itself. I know that's another text form. And this was then some half-baked, not quite C language. But what's funny when people talk about it would be they'd go, oh, wow, is this really modern language? And they would be really impressed with C. And this was sort of, only a few years ago, that C is state of the art. This is the modern real stuff.
Yeah.
Like to be C if it could be. And sort of hearing that from a programmer's point of view, where C has basically been vilified for the 10, 20 years at least, and seen as the source of all bugs and evils and security problems and what have you.
Yes.
But still, these strange ecologies where they've grown separately and looking jealously on and have a very different view of of what programming languages are.
Very interesting.
Yeah, so that's roughly embedded control systems. The interesting things are obviously it's very sort of time limited, so it's often strategies for how to break work over multiple sort of time slices. So it's like
real time programming.
Yeah, so it's all hard real time. And if you miss your time slice, then you won't be able to execute that very high frequency algorithm for modulating pitch. That has to be 20 hertz at least.
Yeah, interesting. But so you use some kind of like runtime system, operating system, like it wasn't obviously Linux, it was something else, like some RTOS.
Yeah, so we used by using C, we then target loads of platforms. So did do real-time Linux, did do real-time DOS even, yay. Yeah. I actually had to pull out a disk of DOS 1 point something, we actually had versions like this, amazing.
I never heard that it exists.
I know, it is a different world, but that would be modern for a, so did use more VxWorks, so that's the thing that's on Mars landers, QNX, Windows C, and then a lot of proprietary platforms like GFANUC and Siemens and Omron and Bachmann.
Okay. No.
And
sounds like an Arabic name.
Yeah, and that was one of the roles of the sort of code generation, was that you could basically change the generation templates to create all the different bindings for different platforms. So it was one of the sort of platform strategies was to be able to regenerate a lot of the, it would just be unbelievable to have handwritten signal management for each platform. But I'm pretty sure that's what some people actually do. Crazy.
Yeah, but you see, you had some kind of problem, and you basically what you created is some kind of special language that you write in tables.
Yeah, and it generates the same scene images and all the code. And that's why when people say I'm not sure about what sort of problem I want to solve, is they sort of try and do some real work almost, and the problems will find you. It's
right.
And then that's where you have no alternative to fix them. So a related software tool that I quite liked was that. So I made something called a hardware in the loop testing tool. So I was really into unit testing, and I'd loved sort of test-driven development. It was sort of newer back then. I know people have mixed opinions, but I still think it's fantastic, especially within IDEs and things where you can just quickly invoke any function and test it. That's the rebels to me. But the problem with an embedded control system is that you can't do that. You get this horrendous long download time into a machine, and then we've got all these inputs that aren't plugged into generators. It's like, well, is this going to work? And how are you going to test it?
I always wanted to ask this question while I was listening to you.
So the way to test it by creating this tool, and it's called hardware in the loop because it's basically sort of a simulation of all the stuff that you don't have. So the generator and the pitch systems and the wind and everything else. And then you have your control system, and you then plug it, you fake all the inputs. So,
fake? But
well, simulate. So that was one of the big products of the company, was a wind turbine simulation. So we could actually simulate the real physical hardware and all the whole vibrations and how it behaves. So the really difficult stuff. So this was the real knowledge of the company, was how to simulate wind turbines. I then turned it into a real-time model so that it could run at sort of 20 hertz. So it meant it wasn't as fancy as the one used for load calculations. So in the main design tool, we'd be testing control algorithms at a more analytical level. Whereas in this hardware in the loop tool, we're then running it in real time against the control system, and then simulating all the wind and the inputs. but then we basically want the equivalent of a unit test.
Mm-hmm.
And so this tool was then a way to write a unit test for a real-time system. So it would sort of set up the initial conditions,
Mm-hmm.
trigger an event, a rotor over speed, and then ensure that the control system shut down the wind turbine.
Mm-hmm.
So sort of difference from something like N unit or X unit, J unit, all those sorts of unit
Mm-hmm.
testing frameworks is that obviously it's sort of running in parallel to the control system and it's sampling inputs. So instead of saying, is this equal to that? It's more along the lines of wait until this equals that, or this should equal that in 1 second or so. So sampling real-time values. And when people talk about creating programming languages, this is where I have a bad disease of accidentally creating programming languages, which I don't mean to. So this was effectively a projectional editor for a unit testing script, because obviously you had to set up these real-time test plans, and it had a GUI rather than text, and after a while you realize that your unit test plans basically need to be Turing powerful anyway, so you might need to go in loops and check that you can repeat something and all these sorts of things and all the conditionals. So it's basically a dedicated real-time programming language, real-time testing programming language for systems.
Yeah. Interesting. I was thinking about one problem some time ago. I was thinking like, for example, if you have a programmer who tried to solve some kind of problem, and he spent a lot of time, he written a program, then he suddenly lost the code, but he still has everything in his head. He can write down program pretty quickly. It's like it's really just laying out the image that you already have. And if, for example, you write really good specification and also give to some other programmer, they also can write down an implementation sort of quickly. So it seems like the slowest thing during the programming is the clear description of desired behavior or something like that. So something that the programmer has in his head, but it's not on the paper. It's not. And I thought maybe there might be some kind of environment, language, I don't know, where you don't write code, but rather you describe what you want, like vaguely, not rigorously, not too detailed, but you sort of put some kind of borders, laws, what should never happen, what should always happen. And I just thought that if you have that kind of thing, basically then inside this thing, inside those constraints that you created, you can really quickly solve problems and write new code, add new people. And I thought that, I just thought that when you sort of reinvented some kind of language to do, like, when you try to abstract away and create something new, weren't you creating something like that? Like more generic description of what you want.
It sounds like you're sort of describing declarative approaches.
You see, not really. Like if you see what usually people mean about declarative programming, it's still too specific. It's too it needs to be more vague. Seems like so.
Yeah. So it's an interesting topic. So have you ever used any of the constraint solvers or optimizing programming languages?
No.
So they're worth a look. So they're quite elegant. So things I've used in the past have been OPL. That's literally called optimizing programming language. A language whose letters I can never remember. It begins with an A, but it's created by the Orc developer. AMPL. Yeah, and there's sort of Z3 and things are in the same sort of territory. And that's along those lines where you're effectively describing the constraints, literally, and the goal function, and then you just say, go do it, and see what you get. So, how it approaches to something as general as software. So my reaction to what you were talking about was that the developer who could quickly rewrite something they'd lost the code for me, it's not that they knew the specification and what it was meant to do, it's because they knew how the software was put together. And it's a bit like a chess master having just perfect recall of chessboards, because it's certain patterns. So it's like when I know that if I knew I needed to take a certain approach to solving a software problem, it's like knowing the route through a maze. It's like, okay, it's going to be a real pain to walk through the maze again, but I know it's left, right, and I'm not going to get lost. So that's why I find it easier, but that doesn't, there's still the notion of vague goals. So one phrase I really like for describing software is that it's an activity of pure design. So some people think that when you write software, it's like you're a machine in the factory. Whereas actually, when you write software, you're up in a room designing the machine for the factory. So you're creating blueprints, and then the compiler, and the machine actually running is the rest of the factory. So there isn't a production step; it's pure design. So that means there is no space for vagueness, because that vagueness means that it's precisely the gap you've left describing what you want. And you can't magic that gap, because our goal is to only say the minimum required to get the behavior we want. I think every programming language has always had that goal, say the minimum required to get the result. And it's just that to do that, you have to be clear, explicit, and computers are dumb as hell. so you actually do have to ensure they don't, do whatever they might do if you hadn't told them not to. I think constraint solvers and those sorts of tools are the closest getting to what you have, but they solve a very small subset of problems. The one example that I used one of those in anger was for whatever they're called, European Space Agency. So creating a contact scheduler. So if you have a constellation of satellites, you then have ground stations to communicate with them. And if they're sort of geostationary satellites, then you get sort of different coverage by different ground stations at different time. So your goal for a contact scheduler is to organize which ground station is talking to which satellite at what time to maximize, maybe minimize the least amount of time one satellite has in contact. So that so you're trying to create a schedule of contacts to meet a certain constraint, and it's because you want to talk to all of them as much as you. So that's then an optimization problem, and that's when you pull out these optimization tools. But then, they sound like magic because it's a dedicated sort of scheduling problems, constraints. It sounds like it should be solvable. You hit go, and then it doesn't do anything for 3 hours. And that's because what you really need to do is tell it a lot more about how to try and solve it, because it's still not smart enough to search a problem space efficiently. So you then sort of quantize it and say, okay, time is now in 30-minute blocks or something, and simplify it.
I can maybe give a bit more context, like about this thing that I try to describe. What I realized during my work that programmers don't write much documentation, because it's really, I don't know, for some reason people hate it first. Second, it really gets obsolete quickly. Basically, you have some kind of piece of something that references something, and those links break all the time. And it's not well connected. And I thought, okay, what if we could make it somewhat structured. And then I realized, well, if it's already some kind of structure, documentation, probably it should tightly connect to code, so it won't get obsolete. So it has to depend on code, and code should depend on documentation to the point that it's always going to be updated, because people need to check that it's connected. Otherwise, it's not going to work. And this way, if we have some kind of vague system that put constraints, it becomes some kind of structured documentation that you can trust, and maybe it's useful to write because it helps to structure your system.
Mm-hmm.
Yeah, that's how I came to this thing. But I tried to search for what kind of logic language it should be written. It's really, I don't understand. I'm really lost. What kind of logic may fit here? Yeah.
So to describe behavior,
yeah,
to function as documentation. My own opinion, and I know a lot of people don't like this, but that code can be self-describing. That a really well-designed piece of software, I can look at the folders in which the source code is put, and I understand its top-level architecture. I look at the file names, I understand, how each high-level module is structured. And then, I open a file and I see exactly what I'm expecting from the text, and then I can read the text and understand precisely what it's trying to do from beautiful variable names and function names. To me,
that takes a lot of self-discipline.
Yeah, I think because I love the phrase of sort of when people say, "Oh, you should write more comments to explain code that is difficult to understand." I think Kevin Henney says it. He says, if somebody can't write easy to understand code, why on earth do you think they would write easy to understand comments? So the same thing is documentation. Yeah. If you can't express yourself well in code, it's a similar problem in documentation.
Mm-hmm.
There's one thing worse than a developer who writes no documentation. It's the one that writes gargantuan quantities of it, by the way, who never gets around to doing the code because they just love creating architectural documents that never end. Right, okay, so back to your problem. So it does sound like there's always been various sort of prototypes for example, defining contracts over methods and things.
Mm-hmm. Yeah.
And then there's various ways of stating the sort of the input and output constraints and sort of the expected behavior. So if you want to go at the extreme end, I suppose it's things like TLA plus. It's the formal verification languages.
Mm-hmm.
They are basically theorem provers.
Mm-hmm.
But they're a way to, what their goal is to formally prove the language. But I think if there was a radical step to make in that type of direction, it would be to make formal verification something natural and accessible to a novice programmer. Yeah, that would then
sounds like a lot of pain.
At the moment, it's just a scary ass topic that 20 years experience isn't enough. You need 20 years academic experience almost.
I think I should probably. I think I'm stuck because I couldn't clearly describe what kind of scenario I would like to have. And
Yeah, so I'll just tick off the other things I had in mind. Behavioral testing. There's various ways of creating sort of tests that in order to test the behavior, and there are some languages about that. The Microsoft research has a lot of these. I think patterns and practices group. You'll probably find a lot of these ideas about contracts and things. But they're all in a category of idea where you had a problem to write a piece of software, and now you introduce this new technology, and now you've got two problems. You've got to write the software and you've got to do this other thing. And it didn't actually help you get to the end point of good software.
Yeah.
if anything slows you down. That's the real tricky thing. Obviously, it's all in the category of literate programming type things, which I'm sure you've seen. Literate programming.
Yeah, no. I just couldn't pronounce.
Sorry.
Literate programming. Yeah.
Yeah, that's the Don Knuth stuff, and that's where
I know.
the whole Jupyter Hope, notebooks have come from, really.
Okay. Also, about your Thorny, like, what's pronounced?
Yeah.
You try to, like, some kind of way to like create some kind of structure collaboratively, but like, can you like give how do you see like the scenarios of use, like when it happens, and why? Like, certainly convenient to do some kind of like voting or some kind of decision, but I'm just maybe you have something like, is there something that you want to tell about this project that maybe is not visible from the first glance?
I can try and give a high level sort of explanation of the goal and maybe a couple of the ideas, because I know the website doesn't really explain what I'm trying to do. So the motivation comes from if you imagine if you're in a room sort of trying to design a tricky bit of software with a colleague, you often have a particular problem you're trying to solve, and there's many options to try and solve it. But each of those sort of options triggers new questions with new problems to solve.
Yeah.
And and that applies to all of those options, and then all of those sort of options. So you get this big sort of tree you're trying to sort of explore of all these problems. But it's not just sort of a tree that breaks down. Sort of suddenly all the problems interact in subtle ways.
Yeah.
And and it becomes one big sort of complicated ball. So the best engineers I've worked with are people who can keep the largest tree of possibilities alive in their mind and talk about it at the same time. There's a lot of engineers, the average engineer will struggle. They'll have a very limited sort of size of possibilities they can possibly manage at one time. And it's very exhausting to keep this multi-dimensional massive set of possibilities up in the air. But that's also how you get great design, is to basically not commit early and explore this space as quickly as you can in breadth and in depth. So the relationship with future coding is that it's basically, I believe, sort of decision making for this sort of design type problem is about managing complexity. It's often working memory that is effectively the limitation. So you've probably had this experience if you design a tricky bit of software. You think for half an hour, exploring problems, and you've lost your thread. You can't quite remember where you started. It's just too big a problem for one time. And I believe there's a lot of ideas and a lot of designs that are just too big for us to really think about.
Don't fit.
Imagine the world of possible ideas. There's this little tiny corner of things we can actually think about. So it's huge, much larger space of interesting ideas that we can't explore because of this complexity. And I'm desperate to explore that space, and trying to do it causes me great physical pain. Not trying to forget where I am and trying to explore all these things in search of great things. And Thorny is basically a tool to try and help manage complexity and explore it. So the basic idea is that it's a knowledge graph to capture what you do know, but instead of typical knowledge graph is simply facts and relationships. The thing is that it contains questions, so it's possibilities. So it would be, instead of knowing, there's going to be terrible examples, do apologize, it's getting late here. In terms of, it might be, my pet might be in my knowledge graph, but I haven't chosen what pet to get. So it might be a cat, alligator, whatever. This is an open set of possibilities. So my knowledge graph is actually have many possibilities, and and other questions might be more about belief. So it's actually a belief network where I believe Postgres is a great database. Not sure how this is going to relate to my pet, so I'm mixing all my examples. So there are things we're uncertain of, and there are things that we're trying to solve, and there's goals we're trying to achieve, and they're all interconnected into this large sort of knowledge graph. So I'm a bit skeptical of visual approaches. So the way of actually editing this knowledge graph is more akin to an outliner, because I love the flow you get in simple bullet point lists. So it's the things that workflow is known for, and many other outliners. So the outliner functions basically as a way to try and capture your reasoning. So the goal is to capture informal reasoning. So there's a lot of sort of a theory about reasoning, and sort of you don't want to be sat there writing predicate calculus. That's not really how we make decisions and how we choose what is best. It's more of an abductive approach with weighing the strength of reasons and confidence levels. So the goal isn't to be a formal system, but to really reflect how we naturally approach something, so we can just sort of spill out our thinking, and then the tool sort of looks after it for us. So it's there's types of tools called belief revision systems. So it's the way that belief revision, so that we can change our opinion of a fact, and then the consequences ripple through all the inferred issues related to that fact. So this is a bit like functional reactive programming. Change one thing, ripple.
Interesting. I've never heard about it.
Yeah, as a piece of software, it means it's a bit like a spreadsheet that all the cells interact, but they're actually parts of our reasoning instead of parts of our yearly accounts, which is boring. Now it's actually sort of the network of our thinking. So it isn't tables; it's more of a graph. And yes, so that's roughly it. And it comes from a couple of sort of the keys of beliefs I have, which differ with some people. Is that a lot of people think decision making is effectively a calculation, where a better decision is a more accurate calculation, and that a decision has a fixed frame. For me, a decision is an open problem, and the best outcome of that decision is actually from creativity. So it's not A, B, or C. It's, well, hang on, if we step back and think, how can we avoid this decision entirely and go an entirely different route that actually puts us on a path to discovering something brand new. So decisions don't. It's creativity. It's instead of framing things into yes/no questions, it's always saying, okay, so if we're sick of our job, it isn't leave or don't leave. It's maybe do a sabbatical, or try a work shadow, or ask for a move department, or there's actually millions of different possibilities, and it's often discovering the possibility which is the key to the decision. It's not some perfect calculation of certainty, which is sadly how decision science is often framed. There's another thing which slipped my mind. It's related to creativity. Yes, yeah. So the sort of framing of decision. Another sort of typical thing is to treat. If you're solving a design decision in your piece of software, you identify your criteria. Let's say your requirements. That might be the traditional thing. You have your requirements, and that's effectively your goals. So now you're solving this problem for your requirements, and this seems like a nice closed problem. But the reality is that isn't how good software gets designed. There's this interaction between what is possible and what your requirements are. So if you suddenly discover it's actually possible to do something much more ambitious than your requirements, and you often discover that during the design process or during the implementation, then you should change your requirements and go in this direction. Equally, you might have a fixed, absolute must absolutely do this. It must be a fixed budget. And if you find you can't do it, then you drop it. So this framing of how goals or requirements or criteria over decisions the reality is that those are decisions themselves. So you're choosing what your requirements are.
Yeah, yeah.
So that means a decision is framed by other decisions. And how are you going to choose those requirements? So it regresses in various ways. So realizing that your goals are choices changes what a decision is. It becomes quite a ridiculously open, complicated problem, but that's one I want to make easy.
Okay. Yeah, interesting. I'm thinking about it, and I just realized that I have no idea how people think. Like how structurally it happens, and so I could design something that helps it. Because I sort of think, but how exactly I do it? Like, is there some kind of tree that I walk when I do it, or how I return? Is there something emerging? Like, what's happening? It's, if there was a clear model of what's happening when we think, probably would make a proper tool for it, like proper map that resembles.
Yeah, it's so that is certainly one of the goals of the tool, is that it isn't something that takes you. So common sort of decision making tools, they walk you through the steps. You know, first do this, then do that, do that. So it's a fixed process. You know? Yeah. Set your criteria, choose your options, set the numbers, done. You're done. That's your process. So Thorny is aiming to be more the case of, you know, add some options, now add some requirements, now add some options, now add some reasons. Yeah, it just, your mind sort of, the things that pop up in your mind, you know, there's no real rhyme or reason. So you just want to act on them immediately and put them in the right place. That's the sort of the Thorny goal. But when I've done your typical sort of user testing, what people want and assume they want, let's say, is that they want this template. They want to be told how to think, is some people's approach. They say, you know, I just want a repeatable way, and I want to control how my colleague thinks as well, you know. So I want a decision-making tool that's a form of governance, controls. Whereas I want it to be more of a rocket pack, so that however you do actually think, you can just do it a lot faster and cover a lot more ground. And
but as far as I understand, people just have like different personalities, different creativity, like traits, and some people really hate solving like ambiguous creative tasks. They need something like steps that to follow to make it easier. So the other people just hate that kind of work where you have to just follow steps. So it depends from who you designing this tool.
Yes, yeah. I think it's a great point, and I think it applies to sort of programming language design as well. It's because it's when you manage programmers, that's quite a shock. I don't know whether you've done this, but I thought becoming a manager, I'd be a great manager because I'd be the manager I wanted, you know. And so you do that, and then you suddenly realize, no, this is a disaster. It's like the golden rule, is it's called, you know, treat other people as you want to be treated.
Yeah.
It's a lie. It's bogus. Other people need something you don't want, you know. So you get the person who doesn't want to be told specifics, wants to be given freedom, and you get somebody who wants the specification.
Be
told precisely in detail what it is. And so you've got to be, as a manager, a different person to different people. And maybe that's true of tools as well. So I certainly think Thorny is quite at risk of being my personality turned into software.
But that's good. I think there are many people like you, so
that's right.
At least some.
5% of the world is still a lot of people. One of those dodgy statistics things, because I don't know whether you know sort of Myers-Briggs type personality things. I know it's got scientific dubiousness, but it is effectively the INTP personality type turned into software.
INTP.
Yeah. So that's called the architect personality type.
Okay.
So they're very interested in thinking and the structure of thoughts. So it's like a personality type itself.
Yeah.
Right.
Um, so what other topics?
I feel I've done a lot of talking. Do you want to talk about what you would want your masters to be?
The thing is, it's not masters. I'm going to go for bachelor.
Bachelor.
Yeah, because I didn't have a degree like initially, so I have to start from scratch. Yeah, there's a university in Russia, like recently built, and it's taught in English, and sounds promising. Like, so I don't know. I just have a lot of hope for this kind of path. Because for now, like I'm sort of alone. Like I work in a job, and I meet. Actually, I was really happy that when I stumbled upon Future of Code community, really, because finally someone who really worry about that kind of problems. Like nobody cares around. Like really, it's like I was so happy to find this community, and yeah, I'm just hoping that getting into university, I could find more people or like get people interested in that kind of thing, and I don't know, start new religion or company or whatever. But do something, and I need some kind of an environment, and I think this might be it.
Yeah, it's interesting. Yeah. I know that. I think in the UK, if there might be sort of if your goal was to go into academia, I'd make sure you talk to a lot of academics because a lot of them aren't very happy. So make sure you really know what it's like. But
you mean not very happy being academic?
Yeah. Because when I thought about returning to sort of academia, I went and sort of visited a bunch of PhD students, and I sort of discussed what I was doing in my day job. And I saw them, and my idea was applying computer science to sort of genetics, basically. And this was at the Sanger Institute in Cambridge, and all the PhD candidates were so miserable. And they said, "We have no idea why you would want to stop doing what you're doing and come do this. You know, this is not fun." And I found that quite shocking. But yeah.
Okay. Well,
but think about it. There was what I was going to say was that for somebody with industry experience in the UK, there's often like you'd be able to skip some of the masters if some of the bachelor if to go into a master's program. You get a diploma. I think they would call it here a diploma. So it'd be like 1 year of a bachelor's, intended to take somebody with industry experience or experience from another subject into a master's program. So there might be more efficient paths than doing a full sort of 3 or 4 year bachelor before doing the next step, given you've got so much practical experience.
Okay, I just is it really possible? Like, I just was looking for it, and I got the idea that you have to start from like bachelor.
I believe so. It's only true for people transferring from other subjects. I know sometimes people can be a bit funny just about letters, credentials, but I think it's certainly the sort of thing to contact sort of admissions of the places you're interested in, and just talk through. This is back to decision making, all the possible options. It's like an option that saves you 2 years of your life. Career. Hey, that's great. It is what made me wonder a bit is this is increasingly rare for software people to even do the bachelor's. So the last software developer I met, they were out of one of these boot camps. They're a professional programmer, and I talk to people without bachelor's, and I have asked them sort of, do you feel you missed something by not having a bachelor's? They don't really, and
they don't know what
I study computer science, and I can't really think that studying type theory is really, making my life better as a professional. It's it felt like sort of a maths degree, unrelated, only vaguely related to engineering. So, if you're interested in effectively maths and theory, computer science is a thing to study.
Okay.
If you want to create programming languages, then I personally believe you should get stuck into industry and get a horrid problem you can only solve by a new programming language.
But do you need to have like time, funding? Like, where are you gonna get it? But in academia, you sort of can.
Yeah, that's true. Yeah, I suppose in the world of time is money, then what you'd be doing is going to San Francisco for a couple of years, get your money, and then come back somewhere and live cheaper.
Yeah, the other problem is that to get to San Francisco, I need a working visa. To get the working visa, I need a degree. So,
right, yeah. I'd be interested in some of the backgrounds because so Yehuda Katz, he was Ruby guy, wasn't he?
Sorry,
I'm getting all the names wrong. So I'm just wondering, sort of, was the Ruby designer in academia?
I'm not sure. He like Yukihiro Matsumoto, Mats.
Yeah.
Yeah, he seems like so.
95. What was he doing in 95? Okay. Yeah. So member of research lab. So yeah. Okay. Yeah. Yeah. You might be quite right.
Well, we'll see. I think it's not going to be a waste because right now I'm not really sure what I want to do in industry. Like in what kind of field I should work to develop further. So I think going back to academia is a good time to experiment and probably find people. Yeah, ideal would be to create some kind of company that use these ideas but who knows? It's too complicated.
I definitely think it's easiest when you have like a domain of interest, such as I was working in renewable energy, so having that sort of category to find problems in instead of a broad one, a deep one. I think that helps if you if you have that type of focus for discovering the problems and finding people who want you to solve them. In terms of sort of not knowing what to do in industry, it's one of the things I found attractive about software is that you can sort of choose. Because as I was saying, I was doing space, which was like my childhood passion, and space gradually became defense. It's sort of, what does this satellite do? We can't tell you. Okay. I don't really want to be working on this. I want to do something good for humanity, so renewable energy. So I was able to sort of get the software interest and the interesting engineering problem, as well as trying to do something in a direction that I thought was useful. So I think that's what I like about software. Quite lucky.
Yeah.
Okay.
Yeah, it's been a while.
Yeah. So that was a great chat. I definitely wish you the very best of luck with getting your bachelor's. If there's anything I can do to help, just send me a message. So,
okay, thank you.
I don't know what I can do, but if it's happy to give it a go.
Yeah, we'll see. I think you're gonna get through and everything will be great.
Okay, right. Well, thank you very much. I guess we'll wrap up. Great.
Okay. It was a pleasure to talk.
Thank you. Bye-bye.
Bye.